Hello, I'm Laurence Howe. This short video is intended to serve as a guide to help you decide whether to adopt DCC or stick with DC. DC is direct current, which means the current flows in one direction only. If the current flows in one direction, the train moves forwards, and if the current is reversed, the train moves in the opposite direction. DCC is digital command control, which is a higher frequency alternating signal that provides both power and instructions to the trains and accessories. I'll consider the two systems one at a time, beginning with DC. Let's start with the basic oval of track. The one shown here actually has 2 points built into it, but we can safely ignore those for now. For a basic oval, the usual method of train control is a simple DC controller, such as the Gauge Master Combi single track controller with a plug-in transformer. The transformer plugs directly into a 13 amp main socket, and a lead from the transformer plugs into the controller. From the controller there are 4 terminals, 2 12-volt DC connections to the track to control the trains, and 2 16-volt AC connections for operating accessories. For the moment we will concentrate on connections to the track. With a simple controller such as this, every train on the track will run if the controller speed is set for a train to run. So you will need to isolate sections of track. This is normally achieved by using insulated rail joiners, or IRJs. Some points connect all the branching tracks together, and some isolate the branching tracks, so it is important to know how your points connect the tracks together. It is only really necessary to isolate one rail, but you need to be careful. It is safer to use IRJs on both rails of a branching track to completely isolate it from the point and the track leading to it. The branching track will need a separate power feed. For a simple controller, a switch is required to connect the isolated section to the controller. A train can be run onto the branching track and then isolated, allowing another train to run on the other track. To allow multiple train operations, more sophisticated controllers can be used with more than one train control. On the accessory front, I will confine my remarks to points. But semaphore signals may be treated in a similar manner, although multi-aspect light signals need a somewhat different approach. For more complicated layouts, to operate points remotely, a point motor is recommended. The simplest type of point motor is one operated by a solenoid. A solenoid requires a relatively large current and throws the point with a bit of a thump. But a solenoid cannot stand current flow for any length of time because the coil would soon burn out. A passing contact switch, or a capacitor discharge unit known as a CDU, is required to give the solenoid a hefty pulse of current that will quickly fall to zero. Once the operating pulse ends, the solenoid exerts no pressure on the point blades. So there may not be good contact between the point blade and the stock rail. The stock rail is the fixed rail that the point blade rests against. The frog is the part of the point where the 2 point blades meet. To ensure a good connection to the point blade, a frog dropper is required. When the points are changed, it may be necessary to change the frog polarity. This means that there will have to be a frog dropper connecting the frog to a switch. The switch must be synchronized with the point motor, or a short circuit may occur. Some solenoid point motors have built-in switches, but because of their simplicity, it is possible for them to be unreliable. On the plus side, solenoid point motors are relatively cheap. Servo-type point motors are greatly favoured amongst some modelers. They require a low current and operate relatively slowly. They are much more robust than solenoid motors, with a typical life expectancy of 100,000 operations. They apply a firm pressure on the point blade once the operation is complete. When used with DC, a separate DC supply between 12 volts and 23 volts is required to power them in addition to the switching connections. Servo point motors are considerably more expensive than solenoid ones. DCC is a completely different approach to model railway electrics, or should I say, model railway electronics. It can greatly simplify layout wiring and train operations. Opinion is divided about DC versus DCC. Some love DCC and others hate it. All that is required is two wires that run all the way around the layout, known as the DCC bus. Every section of track is connected to the DCC bus via droppers, and every accessory is connected to the DCC bus. The controller may look a bit like a black box, but the operator has what is known as a walk-around. Sometimes the controls are on the controller itself, but this is less convenient than a walk-around. Occasionally, multiple walk-arounds may be used, which allows more than one operator to run trains at the same time. Every locomotive, railcar or multiple unit is fitted with a DCC decoder. In many cases, locomotives are DCC ready, which means they have a socket that can accept a DCC decoder. When supplied, the socket contains a blanking plate that is replaced by the decoder. It is becoming more common for locomotives to be DCC fitted, which means that the decoder is already fitted when supplied. Those who hate DCC are generally averse to the need to program each locomotive to run on the layout. In reality, this is quite simple, depending on the type of controller. Once programmed, it is extremely easy to run your trains. There are a few basic rules that need to be followed. Whenever a new decoder is supplied, it always has a loco address of 3. DCC controllers generally have the ability to program on a special programming track or on the main track, in other words, on the layout. So, as long as you remember to avoid loco 3 as an address for any of your locos, any new loco can easily be programmed on the main layout. Using the controller shown, it is a simple matter of selecting the loco by pressing Loco, followed by the loco number, in this case loco 3, then Enter. Then press the Prog button twice, followed by Enter to begin programming. The controller display should indicate loco 3. Press Enter again, and it prompts you to enter the new loco address, which may be anything from 1 to 127, but remember to avoid 3. Enter the new number and then press Enter again. The loco may execute a little jump when you press Enter, depending on the decoder fitted in the loco. The controller then prompts you for a sequence of other values, but you can just keep pressing Enter and then run the loco as you would on DC. You can now run more than one loco at a time on the one walk around by selecting each loco in turn. You can also have two locos on the same track with one running and the other stationary. When programming, you also have the option of setting the acceleration and deceleration rates and the top speed. If you turn the controller up to full speed, the loco will pull away and gradually speed up. If you turn the controller back to 0, the loco will slow down to a stop again. There is also the option to configure two locos as a double header. If a point motor is a solenoid or a non-digital servo, it will require an accessory decoder. When I first began Martin Hinmarch, I used solenoids and fitted these DigiCages decoders, each of which controlled 8 points. But for example, with Cobalt Digital IP turnout motors, each motor requires just 2 wires connecting to the DCC bus. Each type of decoder will have its own set of instructions for programming. Generally, they are quite simple to program, although it may take a little time to get the hang of it. Once a decoder has been programmed, it can be operated from the walk around by pressing the accessory button followed by the accessory number and then enter. The point can then be controlled by pressing 1 or 2 to switch it one way or the other. But the really significant gain is the ability to set routes. This is a plan of my Martin Hinmarch layout. There are 47 points, all of which are numbered on the plan. The first advantage of DCC here is that I have been able to give both points of a crossover the same ID, so points 39 and 40 both have the ID 39. When accessory 39 is selected, both parts of the crossover will operate in synchronism. The route setting diagram shows how several points are grouped together as a route. This enables me to run a train from one set of storage loops round to the other with a single route setting. I press the route button followed by 1 and enter, then 1 plus route 2, enter and 1. The trains in loops 5 and 15 can then run through the station and change places in the loops. This fragment of the operational timetable gives an idea of the simplicity of train and point control. I hope this little video has been of some help to you, whether you are a complete beginner or considering branching out into N-gauge to expand your layout. It may help you decide whether you would like to use the traditional DC approach or take the plunge with DCC. Whatever stage you have reached so far, I hope that you will continue to develop your layout and wish you happy modelling.